Let's talk a little bit about banked corners. Um, so before we talk about the force at an angle and all this stuff, right? Let's talk about the simplest possible situation. So let's imagine that we've got this flat surface and we've got some object sitting on a car or something like that, right? We could do better than that. We've got a flat surface, we've got a car, right? Okay, and this car is coming around a corner, but the corner is dead level. Here, we'll draw the car in here. There we go. This is like my car. Okay. Understand that the velocity is, of course, kind of like this, right? Okay, but there's a sideways force, a force toward the center, and this, if it's a totally level surface, gravity pulls this thing straight down. The surface just simply pushes up like that, okay? So the surface itself doesn't help you at all, except that it causes friction. It pushes against the tires of your car and causes friction, and the centripetal force you get totally from that friction, okay? The surface doesn't help you in any other way. Now, if you imagine that we are on a banked surface, remember that the surface presses perpendicular to it, right? So this is the reaction force of the road. Okay. Now the interesting thing about that is that that has two components, right? It's got a component toward the center, right? This helps you get around the corner, right? This helps you go around, right? You go. Okay, this helps you go around, and then of course you need an upward component to hold up the car, right? Hold the car up against gravity, right? Okay, so just by tilting the road like this, right, we get a component of force just from the surface of the road pressing against the car that pushes toward the middle, and then we also have one that's upward like that. Now, obviously, if we get this to be mv squared over r, that is a centripetal force, right? If we get it to be that, and we get this to be mg, the force of gravity, right? That angle is the same as this angle. These guys are congruent. Okay, and so that angle right there is the inverse tan of opposite, so mv squared over r divided by mg. Need to make that a little bigger, right? Now the m's go away, so a car that's, a corner that's banked ideally and optimally and perfectly for an Audi would also work for a semi-truck if they're daring enough to go that fast, right? And so this ends up being tan minus 1 of v squared over rg, right? Where this is our radius of curvature, this is gravity, this is the velocity. Now understand that this, if we bank the corner this way, we actually don't have to turn the steering wheel. We don't need sideways friction. The surface itself makes you go around the corner. So it's a bit like we used to make saucer sled runs where the cross section of the curve was like the bank of the curve was actually had this curved cross section to it, just like bobsled runs in the Olympics, right? They've got a variation of bank angle, and they have the same thing here, right? It gets steeper and steeper as they go up this wall. There's also in Southwest Portland, near where I live, they've got this velodrome where they've got the wall is curved like that, right? And honest to God, you're biking out. If you can go, I think it's like 45 miles per hour, you're just like almost sideways on this wall. It's not as steep as I drew it there, but it's really pretty exciting. The Alpenrose Velodrome. Anyway, what I'm going to do is in the next few examples, I'll just show you how to use this formula.